Kestrel predicted the last 3 months of delivery times to within 2 minutes on average, and then missed its first real week by 19. Nothing broke. No data was lost. The pipeline ran green all night, every night. The model simply became a different model the moment it met a week it had not already seen. So what changed between Friday and Monday? Hold that question. We will come back to it at the very end, because the answer is the whole difference between a model that has learned something and a model that has only memorized something. Here is the sentence you have probably said out loud in a review, or read in a blog post, or nodded along to without examining. Kestrel is overfitting because the model is too complex. Simple. And it feels like it explains everything you just saw. But we should really avoid defining a failure by the thing it superficially resembles. Complexity is not the mechanism. Ask yourself this. Is a forest of 500 decision trees simple? It carries hundreds of thousands of decision nodes, far more than the single tree that just failed you, and it is famously difficult to make it overfit. If complexity were the cause, that thing would be the worst offender in the whole field, and instead it is one of the best behaved predictors anyone has ever shipped. So the explanation cannot be complexity, and you should be suspicious of yourself for accepting it for so long. Let us try again. Maybe overfitting is when your training error is low and your test error is high. That is certainly true of Kestrel. 2 minutes on the data it was built from, 19 minutes on the week it had never seen. Does that definition help you though? It names the symptom you already measured. It does not tell you which knob to turn on Monday morning, and it does not tell you whether turning that knob will help or hurt. A definition you cannot act on is a label, never the explanation. Let us try this one more time. Take the error apart instead of labeling it. When your model makes a prediction and reality supplies the answer, the gap between them is not one thing. It is 3 things stacked on top of each other, and they behave completely differently. The first is bias. Bias is the error you would still be making if somebody handed you infinite training data. It is the part of the world your model is not shaped to represent. If you predict every delivery takes 31 minutes, you will be wrong about rush hour forever, and no amount of extra data will rescue you, because the shape you chose cannot bend that way. The second is variance. Variance is how much your prediction moves when you swap one training sample for another sample drawn from the same world. Notice that this has nothing to do with the truth. Could a model be perfectly unbiased and still be useless? Yes, and that is exactly the case worth understanding. A model can have low bias and be violently unstable, and you will never see the instability if you only ever train it once. The third is noise, and you cannot remove it. 2 identical deliveries, same route, same hour, same driver, will differ because somebody double parked. That gap is in the world, not in your model. Note, this decomposition is exact for squared error. The expected squared error at any point equals bias squared plus variance plus the noise floor. That is why it is worth learning rather than treating as a metaphor. It is not a picture of the problem, it is the problem, written down. Can you think of a model you shipped where you never once separated those 3 terms? Most of us can, and that is the honest starting position. Now use it on Kestrel, and watch how differently the question reads. Was Kestrel wrong because it could not represent rush hour? No. It represented rush hour beautifully. It represented that specific Tuesday in February beautifully too. Kestrel was wrong because its answer depended enormously on which jobs happened to land in its training set. That is variance, and variance is invisible to every metric you were looking at. Here is how you would actually see it, and I would encourage you to do this on your own model this week. Retrain Kestrel 12 times on 12 different random halves of last quarter's jobs. Ask all 12 for a prediction on the same Tuesday delivery. If those 12 answers span 40 minutes, you have measured your variance directly, and you no longer have to argue about it in a review. And if all 12 agree closely while still being wrong? Then your problem was never variance at all, and everything you were about to do would have been wasted effort. Analogy, think of 12 surveyors each measuring the same field. If every one of them reports a different acreage, you do not have a hard field, you have a shaky instrument. Averaging their reports helps you. Buying a more sensitive tape measure does not, and may make it worse. Now let us build the thing properly, 1/4 step at a time, because every step follows from a number you can measure. Kestrel version 1 predicts the average of every job you have ever recorded. 31 minutes, for everything. Its variance is almost 0, because that average barely moves when you resample your data. Its bias is enormous. Is that a bad model? It is a useless one, certainly, but notice that it is useless in an honest and stable way, and stability is a property you will be paying for later. Kestrel version 2 is a single decision tree, allowed exactly 2 splits. Is it rush hour? Is the drop point above the 4th floor? 4 leaves, 4 numbers. Bias drops immediately, because you have let the model bend where the world bends. Variance rises a little, because now the split point itself depends on your sample. Kestrel version 3 is the version you actually shipped. You let that tree grow until every leaf holds a single job. Your training error goes to 0. Should that have pleased you? It went to 0 by construction, not by insight, and those are very different achievements. A leaf holding one job is not a rule about deliveries. It is a memory of one afternoon in February. You have not built a model of the world, you have built a very efficient index of your own history. This is the point where 2 teams inside your company will now disagree, and they will both be partly right. The first team says prune it. Cap the depth, demand 20 jobs in a leaf before you split it, and accept a worse training number in exchange for a stable one. They are trading variance for bias deliberately, and that trade is real. It is also a ceiling. However carefully they tune that single tree, they are choosing one point along a curve, and they can only ever move along it. The second team says keep the deep trees and stop trusting any one of them. Grow many, on slightly different data, and average the answers. This is the move that is genuinely different in kind, because averaging attacks variance without touching bias. Here is why that works, and it is one line of arithmetic. If you average many predictors that each have the same variance, and their errors are independent, the variance of the average falls in proportion to how many you averaged. Each individual tree stays as deep, as greedy and as overconfident as before. The average of them is calm. The mechanism is called bagging, which is short for bootstrap aggregating. For each tree, draw a training set the same size as your original by sampling rows with replacement. Some rows arrive twice, some 3 times, and some do not arrive at all. On average, about 63% of your rows appear in any given bootstrap sample, which means roughly a third of your data is left out of every single tree. Does that sound wasteful to you? It sounded wasteful to me too, and it turns out to be the most useful accident in the whole method. Ask yourself what that leftover third is good for. Those rows are out of sample for that specific tree, so you can score each tree on exactly the rows it never saw, and average those scores across the forest. That is called out-of-bag error, and it is a validation estimate you get for free, without setting a holdout aside. Very few techniques in this field hand you something for nothing, so notice this one when it happens. Now the honest problem with bagging, and this is where random forests earn their name. That neat arithmetic assumed the errors were independent. They are not. Every tree is grown from the same underlying data, using the same greedy rule, so every tree finds the same dominant feature first. If distance to the drop point is the strongest signal in your data, all 500 of your trees split on distance at the root, and then they all make correlated mistakes. Averaging 500 trees that agree with each other buys you almost nothing. Which raises the question that produced the whole method. How do you force trees built from the same data to disagree? Leo Bryman published the answer in 2001, and it is almost rude in its simplicity. At every single split, do not let the tree consider all the features. Show it a small random subset and make it choose the best split from only those. For classification, the usual choice is the square root of the number of features. For regression, it is commonly about a third of them. That is the entire addition, and it is why the method is called a random forest rather than just a bag of trees. The consequence is that when distance is hidden from a particular split, that tree is forced to find its second best story, expressed through time of day, or floor number, or driver experience. Individually, those trees are worse. Their correlation with each other drops sharply, and because correlation is what was capping your benefit from averaging, the forest as a whole gets better while its members get worse. Note, that sentence is worth reading twice, because it is deeply unintuitive and it generalizes far beyond trees. Deliberately weakening each member of one ensemble can strengthen the ensemble as a whole. Have you ever wondered why a committee of narrow specialists outperforms a committee of well-rounded generalists? This is the same arithmetic, and it is doing the same work. Case in point, the Netflix prize was won in 2009 by a blend of many models rather than by a single brilliant one, and the winning margin over a single model came almost entirely from combining predictors that failed in different directions. The same pattern shows up on Kaggle to this day. Diversity of error is a resource, and most teams spend all their effort on accuracy instead. Now compare this with the other family you will be offered, because the contrast is what makes the choice clear. Bagging in random forests grow many strong, independent, deep trees and average away their variance. Boosting, which is what you get from XGBoost and LightGBM, grows many weak, shallow trees in sequence, each one fitting the errors the previous ones left behind. That attacks bias, not variance. Two families, opposite diagnoses, both correct about the failure they were designed for. So here is the practical question you should be asking, and it is not which library is better. Which of your two terms is large? If your model is unstable across resamples, you want averaging. If your model is stable and simply wrong in the same direction every time, averaging identical mistakes will do nothing for you, and you need more capacity or better features. Quick win: before you change a single model, run the 12 resample experiment from earlier and write the spread down. It costs one afternoon, it gives you a number instead of a debate, and it tells you which half of this episode applies to your situation. What is your current answer to that question? If you do not have one, that is the whole task for this week. Now the honest part, because this is where enthusiastic advice usually stops. Caveat: a random forest cannot predict outside the range of what it has seen. Every prediction it makes averages training labels, so if your longest recorded delivery is 90 minutes, will your forest ever say 120? It will not, no matter how extreme the inputs get. If your problem has genuine trend or extrapolation in it, this family is the wrong shape and no amount of tuning will fix that. Caveat: a forest is expensive where it hurts. 500 deep trees is a serious amount of memory at serving time and a real latency cost per request, in exchange for accuracy gains that are sometimes small. Many teams underestimate that bill, and a single pruned tree that a human can read is occasionally the better engineering decision even when it scores worse. Caveat: none of this rescues you from bad features or leakage. If your training data quietly contains a column that will not exist at prediction time, every tree in the forest will find it, all 500 of them will agree, and your out-of-bag error will look wonderful right up until production. Averaging protects you from noise in your sample. It does not protect you from being systematically wrong, and it may still leave you confidently wrong. So let us settle the Monday. Nothing changed between Friday and Monday. That is the point. Kestrel version 3 was a single deep tree whose leaves were memories of specific afternoons, and its answer depended far more on which jobs happened to be in its training set than on anything about the world. Swap the sample and you swap the model. It was not too complex. It was too dependent on its own history, and the 2-minute training number you were so pleased with was not a measurement of skill. It was a measurement of memory. So ask yourself these 5, in this order, before you reach for any library at all. Have you ever retrained your model on a different sample and compared the predictions? If not, you have never measured your variance, and every conversation you have had about overfitting has been guesswork. Is your error stable and wrong, or unstable and wrong? Those two need opposite treatments, and treating one as the other will cost you a quarter. Do your ensemble members actually disagree? If you have not measured the correlation between them, you may be averaging 500 copies of the same opinion. What does your model do at the edge of your data, and can your business tolerate that answer? Because a forest will quietly refuse to extrapolate and will never warn you. And what is your irreducible noise floor? If two identical deliveries differ by 10 minutes in your own records, then chasing a mean error below 10 minutes is not ambition, it is a promise you cannot keep. Answer those 5 and the choice usually makes itself, which is more than most model reviews manage. Sometimes the answer is a forest. Often the answer is that you needed one honest variance measurement and a shallower tree. Which leaves the real question, and it is about your model rather than about Kestrel. The next time a training number looks too good, will you be able to tell whether your model has learned the world, or merely learned your data? That one is your call, and it is cheaper to answer now than to have production answer it for you.